Well, good afternoon, everyone, and thank you for attending the most recent in our Tuesday at 2 public education series. The purpose of Tuesday at 2 is to present innovation in the world of decentralized water resource engineering. Recently, I came across a wonderful YouTube clip of the Australian water environment. I think it was their president, who has a campaign to stop using the word wastewater treatment plants and have them rechristened as water resource recovery facilities, which I think is brilliant. That is exactly what we do. We are not in the business of wasting water. We're in the business of recycling water. That really is the essence of who we are and what we do. I'm your moderator for the day. My name is Jen Best. I'm the Executive Director of Wastewater Education. We began as a local, became a regional, and now we're a national 501c3. You'll see my contact email there, and anyone who was invited to this session received all that information with your confirmation. As usual, you will see at the bottom there our legal disclaimer in that we do provide these sessions for the free exchange of ideas amongst individuals and organizations. The content is not ours. The content belongs to Judd Sundine and BiO2 Solutions. And we should not, and you should not construe the presentation of this as an endorsement or a marketing of that particular technology or that particular proprietary company. But that being said, we would like to welcome Judd. I became aware of this amazing system through our LinkedIn connections, and I see many of you are also LinkedIn participants. Judd, I'm going to let you introduce yourself and let me know when you would like me to advance the slides. Go ahead, Judd.
Okay, Denver, thank you very much. Again, my name is Judd Sundine, and I'm a microalgae specialist with BiO2 Solution based in Colorado. Next slide. And as you can see by our logo, we are powered by algae and approved by nature. And we're sustainable wastewater reuse. And we specialize in lagoon wastewater treatment. It's advanced, innovative, and sustainable. We'll come back to the innovative part right here because this has some implications for later on for funding opportunities and things like that. So we will come back to that at a later time. So I want to thank you again for tuning in to this discussion, and people that really want to advance their knowledge. I really commend you for being on this webinar and taking time out of your day, and I hope you'll get a lot from, learn some new information, and can take this to possibly to some of your clients. Next. Okay, you can, there's some facts about BiO2 Advanced and Innovative Lagoon System. One, you can utilize your existing infrastructure. You don't have to do anything other than what you have. Your lagoon system, you can meet the discharge standards without building mechanical plants. You can reduce your wastewater operating expenses. Everybody wants to reduce their expenses. And best of all, you can make your lagoon into a community asset. Next. Okay, this is a lagoon system in eastern Colorado. It's the finishing cell. This particular town, they were struggling. The town manager was struggling because the local DEQ was forcing them, because they were out of compliance and they had odor problems, they were forcing the town into building a mechanical wastewater plant.
Okay, Judd, we've had a question. If you would mind turning your volume up just a little bit on your microphone.
Oh, yes, I will do that. Hold on. 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 Oh, yes, I will do that Okay. Okay, is that any better?
Yeah, that's much better.
Okay, we should still be on page. Okay, Kevin, good. Yeah, let me know if I'll just speak up a little bit more, and hopefully that will be good. So the town was really faced with a dilemma. You know, how do we find the money to build a mechanical plant? So they went to their town engineer and asked him to find a solution for their lagoons. The engineer, since he's working for the town, and we found them and they found us, it was kind of a strange deal, but the bottom line is we were able to do a pilot in eastern Colorado, and we built this in 2008, and we've been in compliance since then. So the town has been in compliance since then. Slide. So the town engineer and really the city manager had the resolve to find a solution. He would not cave in to having built a mechanical plant that they could not afford to build, less, much less to run all the time. Next slide. So we have this is really a good segue here. Because of our eutrophication of our streams, we have I just got a letter today from or an email from an EPA survey, and the title of it is the EPA survey finds more than half of the nation's river and stream miles in poor conditions. I think we all know this, but here are some of the highlights. It says nitrogen and phosphorus are at excessive levels. Streams and rivers are at an increased risk due to decreased vegetation cover and increased human disturbance. Increased bacteria levels. Increased mercury levels. These are just some of the challenges that we're facing, and the EPA and the local DEQs have really been forced to make standards more stringent. We're facing more stringent on in a lot of different areas with nutrients and personal care products and viruses and those types of things. There is also less funding. The USDA and the Department of Local Affairs and the state revolving funds, they're running out of money as well. Not as many projects can be funded, and we'll make the argument today that by putting in the BiO2 system, those funding mechanisms will be able to fund more projects over time. And of course, we're all concerned with electrical costs. Your electrical costs are going to continue to go up. So, before we talk about a sustainable, advanced wastewater reuse, I should have put those different slides in like Denver said, but we all get the point. We want to use our resources and reuse them as much as we can. And when I taught this class about BiO2 over the country, there were a few things I want to cover when we're talking about lagoon systems. Either there'll be some new things or misconceptions that I'd like to just bring up right now before we go on. Slide. Okay, most wastewater treatment lagoons, or a lot of them, a great deal of them, because of the eutrophication and nutrients that are available, there's a bad mat-forming algae. When I said algae or a microalgae specialist, I'd look into the classroom and people would turn green, their eyes would glaze over, and I realized quickly that algae was a bad word. So we had to clear up the misconception about what algae is. There's bad mat-forming algae, and this bad algae is actually a cyanobacteria. Most of it is a cyanobacteria in the lagoon. Next. Now, to contrast that, there's good single-celled microalgae that the BiO2 system utilizes to produce oxygen into the system. Next. The bad algae, some of the characteristics of bad algae, they cause odors, they increase the total suspended solids. At times they excrete toxins, they can clog equipment, and they can shade the lagoon from the lagoon wants to produce lots of oxygen, but it can't because the sun doesn't get into the lagoon and let the good bacteria do what they need to do. Next. The good microalgae that the BiO2 uses are single cell. They do not form mats. They're very quick producers. You can see their population quadruples or triples to quadruples every 24 hours. They swim. And the most important thing is they create a pure oxygen that goes into the lagoon. And there is a symbiotic relationship between this oxygen-producing microalgae and the bacteria that are in the lagoon. In fact, the good bacteria will help, the good bacteria population that's caused by the oxygen production by the microalgae will take the nutrients out of the water so quickly that the mat-forming algae, their strategy has been to sit on top of the lagoon and wait for the nutrients to come to them. So if we create a good environment with microalgae and bacteria, those bacteria can consume the nutrients and actually starve out or compete the mat algae for nutrients. So this results in, number one, weed control and odor control. Next. The other misconception or idea that I like to bring up from the start is air versus oxygen. Is there a difference between air and oxygen? Most of us know that you need a great amount of oxygen in the ecosystem, in the lagoon, to cause the breakdown of the BOD, the waste that's coming into the lagoon. You need oxygen. There's several different ways to get oxygen into that lagoon system. We'll look at a few. Next. Some of the total containment ponds and the ones that don't, lagoons that don't discharge, there's air, they're just open, so there's wind that causes some oxygen to be put into the system. It doesn't go very deep, and the atmospheric air only contains 21% oxygen, so a limited amount of oxygen gets in this way. Next. Mechanical aerators. Travel throughout the country and I see a lot of different kinds of mechanical aerators. The idea is to get oxygen in. Well, they're using atmospheric air to try to transfer that oxygen into the system. I've seen lots of lagoons that have broken aerators. And oftentimes these broken aerators act as an anchor to put new aerators in. They can be very expensive. So the next slide, please. The mechanical aerators, there's high initial cost. The power consumption is a concern. There's continual maintenance. And moreover, there's a limited oxygen transfer that takes place through this mechanical type aeration. Next. So the BiO2 solution uses multi-species microalgae, and we introduce that into the primary lagoon, and we create an 18 to 24 inch biomass in that lagoon, and we use a mixing system. We'll get more into that. Next. So the microalgae that BiO2 uses, we just call them biological aerators. There's a low initial cost. The low power requirement, they're just powered by the sun. And most importantly, pure oxygen is infused into the lagoon. There's no transfer efficiencies involved. as with mechanical systems. Next slide, please. I noticed that Kevin has a little bit of delay, so I'll wait a little bit after each slide. Okay, the microalgae fueled by photosynthesis. That's our power source. It's not off the grid, so the power source for what they do and how they populate and repopulate is driven by photosynthesis. Next. There is a symbiotic relationship between the microalgae that's producing pure oxygen and the bacteria that's in there to consume the waste. We have the influent from the town that goes into the primary lagoon. Those are the organics. There's bacteria that consume the organics, and so you have the influent that comes in, organics. You have bacteria that consume those organics, and they give off, in turn, carbon dioxide. They're an animal. So they produce the carbon dioxide that microalgae needs. Microalgae is a plant. They require CO2. They require sunlight, which they have plenty of. And in turn, they create more cells. And these new cells create what? More oxygen. So the bacteria have more oxygen. The microalgae have more carbon dioxide. So you have this circle of life and a great ecosystem within the lagoon. I'll let you look at that for a few minutes and we'll go on to the next. Okay? Next slide.
Let's just wait a second here to let Kevin's connection catch up with him.
Okay. Yes, and my contact information as well. We can get you information on this system as well. So again, this is our finishing cell in Eastern Colorado project we use as a pilot. We were fortunate enough to have the opportunity to put this in. And next slide. We're going to take kind of a 30,000 square foot look at, not square foot, I'm sorry, 30,000 feet elevation look at the BiO2 system. And this just be a quick overview, and then we'll go into more detail. And again, if you have a question, feel free to raise your hand. If we're going to cover it, I'll tell you we're going to cover it, and but we'll just try this. So this is the quick overview. Next. We have the lagoon where the waste comes in, and on the right there is what we call the biological control center. This is the heart of the system. This is where the microalgae is cultured and grown. Next. Inside the biological center are photobioreactors. The blue tanks have our assemblage of microalgae where they're grown, and through a system of a manifold system, they're introduced into the primary lagoon. Next. From the distribution tank in the control center into the primary lagoon, then we have some gentle mixing that occurs to help keep the algae, the microalgae, and bacteria in suspension. Next. So from the finishing cell, the water then goes to advanced treatment called electrodeulation. And then from there, the water is discharged into the waterway. Next. So we'll take a closer look. That was just a quick overview. I know you probably have questions. But the wastewater from the town enters the primary lagoon. This lagoon happens to be one we're working with in Oklahoma. Next. The Biological Control Center meets all U.S. building codes, and the ones we have up have withstood hail and 100-mile-an-hour plus winds. They're engineered to withstand a lot of weather types and have not had any problems whatsoever so far. Next. Okay, inside we have the photobioreactors. This is where the microalgae is cultured. It grows very quickly. We have a filtered water supply from the town that comes in. If it's chlorinated, we have filters that take out the chlorine, because microalgae don't like chlorine, but we have fresh water come into each bioreactor. Next. We have lights for high pressure sodium, ultraviolet, and we're working on a few different things to experiment with some LED lighting, that type of thing, to try to keep the cost down on everything we do. And I noticed, Dendra, some of our slides are a little bit off or weird. They're just coming across this way, so I apologize if it looks like the photobioreactor at the bottom should be on one line, but it's on two actually. But that's okay. We're just getting the idea. Okay. In each bioreactor, then the fresh water comes in, the microalgae grow, and then exits out the side of the bioreactor and goes into a line, and it's gravity fed. Next.
Actually, if you don't mind taking a couple of questions, Judd. You'll see in the chat window there's one from Kevin and one from Roy.
Okay. The one I see now, which one, let's see, are the items in the primary lagoon where the algae is being introduced some sort of mixer? If you mean once it goes, this microalgae goes into the primary lagoon, we do have a mixing system. It's primarily to keep the microalgae in suspension. We'll cover this a little bit later. And to keep the organic matter in suspension and the bacteria in suspension. So we do use a mixing system as well. And we'll go over that in a few minutes. Okay, the next question, let's see. Can you use recycled water from treatment effluent? That's a very, very good question. Since we do have an advanced system at the end called electrocoagulation, we can take that water and reuse it. So we'll discuss more details how it can be reused, but that's a very good question. Most of the systems that we use, the water has to go back into the streams. Like here in Colorado, you have a one-use law. You can use it once, has to go back into the river. There are some places like Missouri, you can use it as many times as you want. So each individual case can be looked at. Okay, but the short answer is yes.
A question before that from Kevin. He was asking what the primary algal genera are in the assemblage.
Well, that's a good question. As part of the patent and part of our we don't want to call it black box technology because we're open for what we do, but there's an assemblage, and each assemblage is really different in different parts of the country. We start with that's a good slide because the microalgae then goes along the distribution tank. But the multi-species, we don't want to use a monoculture. If something kills or something happens to the algae that's in there, then we have more than one species that will pick up the pace for oxygen production. During the day, we get well over 25 to 30 DO or dissolved oxygen readings. And so we really know the tanks are working because we get lots of oxygen in those tanks. So the multi-species, we can't really tell you exactly which strains they are. They're common strains. They're strains that occur in every state. So we look for oxygen production as opposed to a microalgae that produces lipids for biofuels. We're strictly in the oxygen-producing mode. I hope that answers your question. You can follow up with another question if you need
Judd,
to.
are you happy taking questions as we go along here, or do you want to hold them and take a pause in your presentation? It's really up to you.
We can take the questions. If we're going to cover them, I'll just say we'll cover that in a few minutes and be sure that your question is answered.
Keep one eye on the chat window then as they come in. There are a couple in there now.
Okay. Okay. Is this from Jim? The lagoon mixers appear to be microbubble diffusers. Are they? And how much O2 do they add per day per square foot? Okay, that's a very good question. The microbubble diffusers, again, we're going to show that here in a few minutes. We don't rely on that to add any pounds of oxygen to the system. It does, but we rely on the microalgae. And those mixers are used strictly to keep the microalgae toward the top of the lagoon to take advantage of the photosynthesis. It keeps the bacteria and the organics. It helps keep sludge levels, the organic sludge levels, at a minimum because there's more exposure to those organics to the bacteria because there's a critical mass of oxygen, critical mass of bacteria in that 18 to 24 inch zone. So we don't really count the pounds of O2 provided by the micro diffusers. They do, but we don't count
how
them.
do you remove the excess of algae, or is there such a thing as an excess of algae?
That will come later as well. We'll discuss that here, and if we don't touch on that, let's ask that again. I'm looking at the question: how do you remove the excess algae production? Okay, that's a good question. We will cover that because the short answer to that, there is really no excess algae production. It's all used up in the primary lagoon, and most of it's used up in the secondary lagoon. And by the time it gets to the third, there's very little left because there's not as much food left. And we'll cover that. So the microalgae from the bioreactors go to a distribution tank, and you can see right here. That microalgae then goes into the distribution tank. Let me change this a minute. Okay. From the distribution tank, then it fills up and it's on a float switch. And when a certain amount of microalgae gets in the distribution tank, it then goes through a manifold system where it's distributed. It's distributed through weighted distribution lines through a manifold system. So that ensures that the same amount of microalgae is put out, or I call it jettisoned out, into the far end of the lagoon as there is close to the lagoon. So these arrows are not the weighted distribution lines. There's just an illustration to show you how the microalgae goes in different parts of the lagoon. You're getting an even distribution of that microalgae. So part of the distribution system is a laminar mixing fine bubble diffuser, and the microalgae goes to the same points where these diffusers are. so that the microalgae goes out into the lagoon. The mixers take the microalgae and puts it up toward the top for, again, better sunlight, better mixing to get a critical mass of that oxygen for the bacteria. Next. Those mixers can be used, can be driven either from the grid or from solar. And this is a project out in eastern Colorado, again, where they chose to use solar for the mixing system. Next. So laminar mixing, the definition is really a non-turbulent or gentle streamlined flow in parallel layers. Again, we have the microalgae that enters where the microdiffusers are, and at the top you can see those little black things. Those are there just in case there's ever a problem with a diffuser or an algae line. They're tied to those lines, and you can pull them up and do any maintenance or replacement that you may have to. We've never had to do that. But we have those there just in case. Next. So by using this mixing system, it increases the efficiency of the sunlight 200%. We have control of the system with the patent assemblage of microalgae, because we do put in the microalgae on a 24/7 basis. So you have a flow-through event with the lagoon. We're always putting new microalgae in to produce as much oxygen as we can. It also controls the growth of invasive species. So because of our continual introduction of our assemblage into the lagoon, we can control what species are there and how much oxygen is put in. And best of all, because there's so much oxygen that's created, it controls odors in the lagoon. Next. Okay, this is just more about the laminar mixing. So you have a continual exposure to oxygen and the bacteria to consume the BOD and TSS within the wastewater. And again, it's pure oxygen that's produced. Next. So how do we know how many diffusers to put in? Well, it depends on the suspended solids, the total volume of wastewater, but most of all, depending on what part of the country it's in, cold or warm, we have the diffuser placement so we can yield the greatest possible mixing situation and the optimum breakdown of the waste that's in the lagoon. Next. So most of the lagoon systems that we work with are 3 cells. Again, number 1 cell, the waste comes into that cell, and we do most of our mixing, and the microalgae does its work in this first lagoon, and then you have everything going into the second lagoon. If there's any more BOD and TSS, food, we still have the microalgae, we still have sunlight, we still have CO2 from the bacteria, and as it moves down, the waste break down more and more until we go to a finishing cell. It's a quiescent zone, and from there we take the water into advanced treatment. The point on this is we've worked with systems that have as few as 2 lagoons, and we've worked with towns that have up to 19 or 20 lagoons even. So we can take smaller lagoon systems and put curtains in to have more hydraulic retention time, go through those lagoons. There's a lot of things we can do with lagoon systems to supplement what we do with the microalgae.
Question as to whether this would work with just a single lagoon system.
Well, we have to look. That really depends on the size of the lagoon. It depends on the organic load coming in. It depends on how much hydraulic retention time we have to break things down. Most of the time you need a hydraulic retention time is the amount of time once the water enters the lagoon, that a number of days it takes to go out of the end of the system. If you have a very large lagoon, conceivably you could curtain it off and have curtains and baffles and have a quiescent zone all in one, but that would depend on, again, the organic load, and every situation we can look at and see if there's enough time to do that. You need number of days in a lagoon system, mainly because of the fecal coliforms have to be broken down by sunlight, but with our advanced system, we could alleviate that problem with our advanced treatment with electrocoagulation. And we'll talk about that here in the future.
Okay, and there was a question about winter operation, if the lagoon surface is freezing.
Okay. Okay, I'm looking at some of the other questions. Hold on. Okay, during the winter operations, part of the reason we choose, well, we want the optimum mixing situation, so we simply put diffusers closer to each other. Some of them do freeze over, and that's some of the problems with lagoon systems. You have upset conditions, which is part of that is freezing. You don't get the fecal breakdown. Part of it's upset conditions with people dumping septage illegally into the system. There's meth labs that are put in. There's that are flushed down the toilet. There are herbicides, pesticides, those types of things that could really cause havoc to a system. That's another reason we put microalgae in on a 24/7 basis to regenerate that system very quickly. So the freeze problem, we simply put the diffusers closer together, and we have the advanced treatment with EC to ameliorate those problems that we just talked about. So that's a very good question. We can put these in northern climates as well. Denver, was there another question, a quick question? So we could simply use a liquid only diffuser, much like what we use in streams and oceans. I'm not sure I understand that question, but I think on the surface that sounds like it could be, since we don't use the diffuser for oxygen production per se. Anything that would produce a laminar flow, I think, would be okay. Depends on how much liquid it would add to the overall system and how much loading time it would cause. So now we have the finishing cell, and from the finishing cell we have an outflow that goes to the next slide, please. That goes to a finishing cell vault. And again, I apologize for the printing on here. Our original slides aren't like that, but for some reason they are now. The finishing cell vault, this is a picture of a project in Oklahoma before or during construction. The wastewater from the third cell goes into this. There are pumps in there, and next slide shows what the finished vault looks like. You open up that vault and you can see the wastewater and the pumping system is in there. And so from this finishing cell vault, next, we go to our advanced treatment or polishing and disinfection system called electrocoagulation. Most of you probably don't know what electrocoagulation is. So quickly, it's just there's a chamber in the system that has metal plates that are 1/8 of an inch wide or thick, and we have an 1/8 of an inch between each blade. So we create an electrical charge There's usually 217 of these blades in a chamber. We put a positive charge and a negative charge on each end of the chamber, and we take electricity off the grid and we flood the wastewater with electrons. So it allows the suspended matter to become larger particles. And then from there you can go to a secondary separation. There's a lot of different ways to do secondary separation. But some of the ancillary benefits are the EC electrocoagulation breaks emulsions, such as fats, oils, and greases. And it also oxidizes heavy metals. Heavy metals can, in this system, go from or go to an oxide form where they can be put into a regular landfill. So it has a lot of different uses other than disinfection as well. So we'll show some of the results from electrocoagulation. Let's see. Okay. Kevin says, I've seen something similar for chelating metals out of landfill leachate. That's correct. It does a very, very good job on the metal ions and turning them into an oxide form that then can be put back into the landfill. So heavy metals is a really good thing that electrocoagulation does. And there's some different types of electrocoagulation, and you'll learn the differences between some cost more, some cost less. Operating costs, you really have to look at the operating costs to all the machines to really make a good decision on what type you use. But yes, that's a very good question or observation. So the EC chamber has these metal plates, 1/8 of an inch apart, and the water and they're placed parallel to each other. Charge on one side, positive charge one side, negative charge on the other. Next slide. So you have this, let's see here. So you have the water coming up through those plates. Those plates are parallel to each other this way. So the water comes up through those plates, it goes over a weir, and then it goes to a secondary separation. And we most of the time use a tank within a tank that separates everything. Now, because they're larger particles, they settle out very quickly. And so we have a cone bottom tank. The particles go to the bottom, clean water comes to the top, and then out the system. Next. These are the plates that are used. This is a project in Oklahoma again. And you can see the poles that we use for the anode and cathode right here. And then all these metal plates then go between those two plates on each end. And so the water then goes up through, the water is filled with electrons. Next. Some of the things with the BiO2 advanced system for nutrient removal, we have ammonia and nitrates, total phosphorus, TKN, total kilojoule nitrogen. We get some removal rates with those. We're going to talk more about ammonia in our advanced session the day after Earth Day. That will be the 23rd. We have a process we can use with this even in the winter for ammonia especially, and phosphorus especially, where we can use what they call a Struve process. I'll just mention it now, but we can essentially get all the ammonia and all the phosphorus out, and we'll get into that later in a later session. That's a little more advanced than we want to get to here. So for bacteria, E. coli, you can see the influent from the influent to the EC and effluent from the EC. We've gotten a 4-log reduction or 99.99% reduction in most of the bacteria that is in a wastewater system. Next. For industrial wastewater, we've created with BOGs as high as really high BOGs and TSS, and we've gotten the effluent numbers down in the 98-99% reduction as well. Next. Okay. We have viral components. The slide doesn't show that, but it says the removal for viral components, and you can see some of the viruses that is very effective, and we've gone down to non-detect on viruses. The electrocoagulation or the advanced system does a very good job of removing things with, I'm drawing a blank here, I'm sorry. Anyway, we won't go into more detail on the EC unless I'm asked. Anyway, viruses, pharmaceuticals, personal care products. We're doing some research with the University of Southern Florida that is proving out to be very effective on those components as well in the water. Next. Rads, or radioactive materials. It's very effective on radioactive materials. You can get the constituents down, or those down into background levels. They can go into a regular landfill. They'll pass the T-clip test, which is a test that shows what that amount is in a landfill. It shows whether it can go to a landfill or not safely. A non-hazardous landfill. Next. So, to kind of wrap this up, the sustainability of the BiO2 system really hinges on the low capital costs and the low operating costs. Under the capital cost, it utilizes the existing infrastructure. It costs 4 to 5 times less than mechanical treatment plant. As far as operations, it saves energy, and you can keep your existing personnel. So if you have a town that has a C operator, there's no reason to change and get a different operator. The C operator can stay there. It's very sustainable. Next. And really, talk about sustainability. It does help with the upsets in the conditions with icing, illegal dumping. The EC will really even out those year-round events that happen. So let's look at the system capital costs. This was done by a feasibility. It was done by a third-party engineering firm. It was based on 0.3 million gallons per day design flow. The capital costs of BiO2 and the advanced treatment system on the very left is $4.23 per design gallon. And it was studied against a flow-through lagoon and disinfection, a total retention lagoon, and lagoons with slow rate irrigation, aerated lagoons, and an SBR mechanical plant. So you can see of all those, the BiO2 system plus the advanced system was a lot less per design gallon than any of those that they were rated against. The next one is the operating costs. And moreover, the operating costs are very low with the BiO2 system. Of course, you can see here that if we go on the total retention lagoons, right here, the operations cost is very low. On the last slide, Denver, if you want to go back there, the total retention, they're very not inexpensive to build. You need a lot of land because they rely on evaporation, and so you need very large lagoons. So let's go to the next one. But all you do is really just let nature evaporate the water, so your operations cost is going to be less than the BiO2. But compared the BiO2 to a mechanical plant or any of the other systems, the BiO2 system is still very low. And we break this chart out into electrical costs and operations costs and labor. So the number here is the total estimated annual cost. So if we look at these systems with an operations cost and a capital cost. The next slide will show you an overall, it's the capital cost plus a 20-year operations cost. So it's a 20-year life cycle cost. And again, this was determined by a third-party engineering firm based on 0.3 million gallons a day. And the BiO2 system here was much less than any of these others that were studied. So sustainability is a very, very important aspect to the BiO2 system. Next. At the beginning of our program, we talked about innovative technology. There are some funding mechanisms or funding opportunities for innovative technology. And according to the EPA, there are 6 specific criteria which define innovative technology. The life cycle costs need to be reduced by 15%. BiO2 does. The energy requirements must be reduced by at least 20% compared to existing. BiO2 does. Next. There needs to be an improvement in the reliability of and because of the advanced system, we have improved the reliability because of the redundancy that most DEQs require with the advanced treatment and EC. So there is an improvement in the reliability. BiO2 does. And treatment provides for better management of toxic materials. We've talked about metals and Rads and all kinds of toxic materials that come in. EC does that. And finally, the last 2 criteria, the next slide. There needs to be an increased environmental benefit. All that we talked about, the BiO2 does increase the environmental benefits compared to their existing facilities. And the BiO2 here, again, does. So the last one, the technology must improve benefits of joint municipal and industrial wastewater. For those towns that have like meat packing plants and industries dump their waste into the municipal wastewater treatment plant, there has to be increased efficiency in either pre-treatment or something like the BiO2 system, which will help with the capacity of the municipal system that comes in. The BiO2 also does that. So the next slide, to wrap that up. To qualify for approval and funding as innovative technology, the treatment system only has to reach one of those criteria. So the combined system developed by BiO2 meets all 6 of these published criteria. So next one, and we have a question. We're done here, I think. The next slide. Oh, one more. Okay, you're best of all, we have really satisfied the funding mechanisms. If you go back to that one slide, the funding mechanisms have, with the BiO2 system, you can build more BiO2 systems for with the money that's provided. The EPA, you can satisfy a lot what the EPA needs. You can meet the stringent discharge standards. You're more affordable, and the electrical cost and operations cost, it makes you look better because you use a lot less electricity and energy, and you make the town more sustainable. So the best part of this is, the next slide is, your wastewater lagoon can be an asset to your community. Next, and I think that's it. And thank you very much for schlepping through this. I'll answer this question. What are the effluent characteristics of the BiO2 alone? We only have one system that doesn't have the advanced system on it, and it's in eastern Colorado. We have the influent characteristics of the BiO2 alone, in that system, we start with somewhere around 150 to 175 BOD, about the same with TSS, and we've gotten down. They've never been out of compliance since we've been there since 2008, and so we have not been out of compliance. What we're looking at is for that system to add an advanced EC unit for events in the future for icing, for any illegal dumps. They've had a couple problems with fog, fats, oils, and grease. Someone dumped a big source of fat down the drain illegally. It plugged a 15-inch drain, and it caused a lot of problems. And we also had an illegal dumping of an herbicide that killed the whole system. And so with the advanced wastewater and EC, then that will alleviate.
And there was an earlier question asking the, do you get odor from the lagoon when the ice comes off in the spring?
Well, that's a very good question. Because of the mixing system and the bad algae that usually dies out in the winter and goes to the bottom and holds nutrients, and you have turnover and causes odor. Since we don't have any turnover, we don't have any die out, then we have not had that problem with turnover. So there has not been an issue with odors, seasonal odors that's normally associated with lagoon systems.
I guess I'm wondering, if the diffusers are running all the time, does it actually freeze over?
Well, that's why during our design process, if we're in a northern climate, we will put them closer together. So far, we have not had that problem with freezing over, especially the number one lagoon. You have the water is much warmer when it goes in, and if we put the diffusers closer together, we can keep that flowing without freezing. As you get toward the quiescent zone of the third lagoon, then you might have some freezing, but then again, our advanced treatment, because it does such a good job with bacteria and total coliforms and things like that, then we don't have to really worry about if there is an icing situation. So do we have any systems in the northern area? We have one that's about the 40th parallel, so I wouldn't call that north, but we've done some studies of some northern type operations, and so we don't have any in Michigan or Minnesota yet, but we have some great interest that we're looking at doing systems in those areas. There's a question about
dissolved oxygen too, that in the evening when we switch over to respiration, i.e. they consume oxygen and they give off carbon dioxide, does that result in a low dissolved oxygen in the lagoons?
Boy, that's an excellent question. I wish, yeah. Because our microalgae, what we do is we design a system to produce enough microalgae to go out into the system on the 21st of December. So what that means is we have the lighting in the biological control center. We have continual growth. Now, as soon as the microalgae goes into the system and it's dark at night, you're right, they switch over and they consume oxygen. So do the bacteria. And so what happens is we create enough microalgae during the day that we produce really a luxury amount of BO in the lagoons, so that when nighttime comes and all that oxygen is being consumed, here in Colorado we always need to keep a DO reading of 2 and above. And so what we've done is design it so we have in the morning, on the 22nd of December, we have enough dissolved oxygen to satisfy that requirement by CDPHE here in Colorado. So we do create a luxury amount that lasts through the night, and so that's a very good question.
Okay, gentlemen, if you would just hold your questions for 1 second. we are going to close out the recorded part of the session, but we're not going to close the room, and we invite you to stay and actually turn your microphones on and then have a conversation with Judd. I want to thank you all for being a participant. I particularly want to thank Judd Sundine or Sundine. We disagree on many things, ice hockey included, but particularly how to pronounce his name. This is the purpose of wastewater education. We like to use this image because when people say, well, what do you do for a living? And we say we are wastewater education, and their noses turn up, and we say we're not in the wastewater business. We're in the clean water business. There is a reason that the average life expectancy in this country has almost doubled in the last 100 years, and it's because of professionals such as yourselves that we take this business very seriously because we are environmentally aware. We are committed to sustainable future for all the water resources of the planet. And I did want to mention, you go back a slide here, just to remember that the purpose of today was a general introduction to the BiO2 Solution product and their applications and case studies. But if you're looking for much more in-depth information, do join us again on April 23rd as part of our Earth Week celebrations. From 2 to 4 p.m. we are doing a more in-depth engineering session, and we do invite you all to come back and participate in that. And so with that, I'm going to close the recording for the day, but again, do stick around and we will continue to chat with Judd. Thank you so much, Judd, for being a participant for us today.
Thank you for the opportunity. I really appreciate everybody sticking in there with me.